Okay, so let's get started. So here I will use a very short 40 minutes to summarize the recent deep learning trends. It's a very rough and quick survey. So deep learning in essence, we can think about it's really a block, many things composed together, and each one of the block is a differentiable block. As long as you can do the forward step and the backward gradient backward propagation step. So, and then it's building deep learning, it's really similar to Lego building. And this composable and modular property makes deep learning very appealing, but also at the same time very complex. So currently, deep learning has been really dominating inside machine learning, and almost all the top prestigious conferences have the majority of the papers are about deep learning, and also this the influence expanded into all other sub-disciplines in computer science. So the many papers in systems or in software engineering, in security, in just all other parts of computer science have more and more deep learning related topics there. So with such a complex concept and complex family of topics, how would you organize them together? So here is a nutshell. So I normally use this to teach. I use this nutshell to teach my student in my machine learning class. So hopefully next year I will offer a deep learning class, and this is exactly the nutshell I'm going to use to organize the topics. So whenever we, when there's a very complex field, I mean, the simplest way to understand it is to figure out those kind of independent or disentangled variables. So here I extract 7 variables to kind of organize deep learning in seemingly orthogonal or disentangled coordinates. So you can chunk deep learning with regard to the data, kind of data they handle. You can chunk deep learning with regard to this deep learning architecture or topology angle. You can also chunk according to tasks, according to scoring function, according to the search optimization strategy, according to the metrics, and then the last one, it's a little it's kind of like a side of the software perspective, but more and more deep learning has it's kind of pushes the hardware industry is changing a lot. And also I think this is maybe like back and forth because of the advances in the hardware like GPU, deep learning got much more popular, and also and then come back when the current deep learning model is so complex, so people trying to also push them into the edge devices because there are just more and more IoT inside our daily lives. So these are 7 almost orthogonal variables. And so why I'm doing so, and so this is a disclaimer. So it's quite hard to make important topics of deep learning fit on a 1-session schedule. So the reason why I'm doing so is to try to make the student to be able to view a very complex field from a modularity view. And this modularity view can help students to understand, to highlight the most important foundational design choices, why it's about algorithmic design choices, workflow design choices, and what and how and why we learn a certain topic. And the most important is to expose the trade-off in those choices. So I hope this very short session can give you a general overview, but on a much higher level, not about just each specific algorithm, but about more this modularity and why people are doing so. All right, so inside using each of the coordinates or each variable to view the deep learning, and then you can figure out those possible values. I mean, we can chunk the deep learning according to data, like the first variable. You can with regard to this coordinate, you have multiple choices, right? You have multiple values. Now people care a lot, like 2D grade data, which is exactly the imaging data, 1D grade data, which is the audio data or text data, and 3D grade, like virtual reality, all those, they're like spatial information captured, those type of data, graph sets, so on and so forth, and we will talk about them in the following slides, so I will not enumerate every one of the values of each variable, but feel free to check out my slides later. I'm going to share the link later. Okay, so roughly we can think about this, like the 10 trends I selected. The 2 of them are about new data, and they're actually the 2 of them are about a topology, but they are not very new because they were invented. So the CNN and RN in this representation variable, with regard to the representation, they were invented in 1990s, and recently is the transformer just proposed recently. So, but I'm not going to talk more because we have image and we have NLP classes. We have a full class I could talk about this, and we also have a full image class. I think some of you maybe are taking that class, talk about vision type of topology fits there. So what I will quickly go over, it's more about those topics our regular classes don't cover much. So for example, new data types, new tasks, new data type are the graphs, and also maybe programs. The deep learning has a very good like current application on program induction, and new tasks in terms of the generation task, reinforcement learning task. I believe we have a class on that too, but I will talk about that really quickly. There's also this learning to learn task, like you can put a few shots, 0 shots, meta learning all in that category. And inside this, then after that, is the scoring function, the optimization variables, right? So you can actually combine the two, think about they are more like training workflows. And there are many advances, very great breakthrough recently. It's about the training workflows. So for example, this layer-wise pretraining using self-supervised loss function, loss training guides, and second is generative adversarial network, GAN, and then the last is this AutoML, learning to search the topologies. And then after that training module, it's this deployment, is that the 2 last variables. 2 last variable, it's about metrics. So so far, people really push beyond just prediction performance to evaluate the deep learning models. There are a lot more other things people care, like trustworthiness, transparency, probably robust. And the last variable is the hardware. So there are many really exciting work now going on, trying to compress those very good models people already proved work very well, for example, on the ImageNet data set, and to compress them into the edge devices. Okay, so let's get started to each of the trends. So first trend is data. So here we're going to talk about graph, deep learning on graph, and deep learning on program. So essentially on graph, it's about graph data. It's the most like intriguing properties that previous kind of classic neural networks do not handle is this order invariant property. So because a graph, you have this V1 in here, there's a picture here, there's a V1, V2, V3, but you can just permute the order of the node, that's still the same graph, right? So you want a representation learning to be able to figure out, even though there's a kind of order permutation of the node, and the representation of this click, it's still the same. So that's exactly what graph neural network model, this new family of graph neural nets is trying to handle. And there are many important work, for example, graph convolution networks, recent new, like there are just a lot more, like message parsing neural networks, GAT, GCN, and then there are a lot more. So feel free to check out. Even my list here, it's already a little old because this is from 2017 a survey talk. All right, so that's graph data. Graph is about order invariant properties. And then the second trend is about symbolic input. There's some kind of ordering among the symbolic input. So the most classic is program. So there are very good work trying to, like, you feed in the pair. So in this case, you just feed in the input as 2 and 3, output is 5, and you can learn a very good neural networks to perform that sum AB function. And if you think about it, if we have enough input and output, and we truly just can replace programmers, and because our neural network, if can enoughly capable, they can just automatically learn to code. So that's the essence of this group of family of models. So very classic model can do this. It's called a neural Turing machine. So there's a controller module, there's also a memory module, and then there's this writing and reading like head design. So feel free to check out this. There are much more advanced version of this too. This is already a very old, it's relatively older, but it's set up the foundation for this type of sequential symbolic. It's just this kind of NTM can handle sequential symbolic type of reasoning task. So besides computer programs, there's a lot of other type of sequential decision type of data. So like games with symbolic input, they also can be handled by the NTM, this category of models. All right, so that's the new data, there are new data trends. And then now I'm going to skip very quickly about this DNN representation of topology variable, topology coordinates. So even though I segment the data and DNN topology into 2 variables, but actually, in fact, if you look at the history very carefully, and the data and the DNN topology that fits that type of data are very correlated. So for example, great type of data are always convolution nets are the dominating, are the good DNN model you should pick. And language 1D dimensional, now it's dominated by the self-attention-based architecture. Graph is dominated by graph neural nets. Symbolic sequential is dominated by a neural Turing machine type of models. So the most classic, this kind of representation of modules, blocks are convolution, convnets, right? That's for the 2D imaging, and then these attention or self-attention based, or this, the previous like recurrent neural networks, they are very classic. So I will just quickly go over. So essentially, this convnet, it's just learning layers by layer, like more and more abstract features. And it's dominating to almost all the vision input tasks, like for classification, retrieval, detection, segmentation. It's even used in modeling the matrix type of inputs, like in this case, the Go game. And this is a very classic winning of how deep reinforcement learning re-enter the people's eye to got people very excited. So this is only 19 to 19 input vector. In fact, a fully connected feed-forward network can work on this very well. But the AlphaGo paper actually showed very solidly convolution type of topology performs much better than the just basic FCMLP. And then you can also use CNN for the audio data. In this case, we have like time coordinates is one coordinates, the other is the frequency coordinates. And then beyond the CNN, there are also 2 pretty popular blocks called a residue type of connection and also capsule. And the residue type of connection, it's important milestone who enables the ConvNet to be able to train much, much deeper. So feel free to check out this very classic paper in CVPR 2016. I'm pretty sure your vision course already covered all those very much detailed compared to what my skip version. All right, so that's the end. Then let's just talk a little bit about the current NLP model. So in the past 3 years, there are just so many breakthroughs in the deep learning language input. So you may already know this, all those fancy names like Elmo, Transformer, BERT, Glove, and then recently XLNet, Robustness, DistilBERT, and also recently from NVIDIA. Just there's so many advances, and I'm very sure your NLP class covered this because this is a semester's of content. So I will just skip this. And you can draw each one of those into some kind of normalized network view. And this is the RNN, the way to draw the RNN, the way to draw the RSTM, the way to draw the GRU, and a basic attention network. So here is this visualization I really like, and from this link. And this author used normalized symbols to draw all different kinds of network architectures. So feel free to check out this. All right, so that's the network topology. And then you can actually tell there's so many different type of graph topology in the deep neural network zoo, model zoos. So now let's actually jump to tasks, which I will focus a lot more. So in terms of tasks, classic supervised machine learning mostly just focus on regression and classification, and also then plus unsupervised focus on clustering. But deep learning kind of enabled many more, much more exciting tasks. So here I pick only 3. So it's the generation task, reinforcement learning task, and this learning to learn task. So the generation task, we can think about like it's generated by these deep generative models. And we can categorize the generative model into 4 kinds. So the latent variable model based like VAE type, or implicit model based like a GAN type, or transform like nice. If you ever learned about this, you're going to be, I think those term short words you should be able to tell them, and autoregressive based. So essentially, why do you need a generation model? So people talk about like you can use generation model, generative model to do imputation for the missing data, to do simulation for like maybe planning for RL, or maybe some other kind of model output. But so far, actually now, the most people are very fascinated by this realistic generation task. So let's see what is. So the realist generation, so this is more like imputation. So there's, you have a bad image, saved maybe badly on your disk, and you can use various kind of generative models to make them into much better quality. So this is the first possible application of generative model. And then the second type is very interesting, is you can use label to generate a realistic image. So in this case, it's a segmentation plot, and then you can use it to generate very realistic images like on the right. Think about how this will influence the movie, the artist industry, right? Video industry, and also edge to images, the sketches. You have only the sketch, and you can add like texture, color, all those different kinds. And then this actually also will revolutionize the design, right? Manufacturing industry, which is happening now. And then you can do text to image, image to text. All those are very classic generation tasks. And the most I want to talk, like maybe some of you already know, is the DeepFake. So maybe you already played with this. DeepFake is generally understood to be just a video in which the face of one person has been swapped with the face of another person. And there are many variations of this, like they're beyond the face swap, there are puppet master, lip syncing, and this has been used on some very bad uses. But here I only show you the good use. So for example, Facebook trying to use DeepFake like technologies to anonymize the faces. If you don't want to have your faces even talk, but you can just, Facebook use it to do the anonymize face, which is a good use. You can also use this to de-age the face, right? This is also a good use. So it starts from a very small paper, but grows into a really big industry. It's very powerful, but it's also kind of scary. So people spend time, a lot about generation, but also there's also about detection, right? So because of this type of technology, you really don't, you're unsure. You start to question when you look at a video or an image, is that a real person? Is that a real person talking, or it's just a fake one, right? So it's very interesting and a very interesting, exciting application of generation models, but it also causes a lot of ethical concerns. Okay, so the next trend 4, it's still the task, is deep reinforcement learning. So this is ranked as the top 10 breakthrough technology in 2017 by MIT Technology Review. And essentially, if you are in the reinforcement learning class, you already learn much more. So, but let me just give you a really, really rough intro to other students. So reinforcement learning is essentially trying to learn an agent that can interact with the environment. And so it different from the supervised learning, you have the XY pair of supervised signals, but here you may only have the signals after a sequence of action taking. So which makes the task much, much harder than the supervised classification or supervised prediction task, because you have much sparse signals, and also your data, it's not IID. So traditional supervised learning, you have this IID assumption of your samples. But here, because of the sequential nature, so your samples are dependent. And there's also clear classic distribution shift, this issue here. So it's a very hard task. And then there are many important, exciting research are happening on this topic. So deep reinforcement learning essentially just replace this environment map to the action in a deep learning model. So for example, you can just model the observation and the reward and then predict the action. So this is the classic policy net formulation. So the deep reinforcement learning got popular actually from the AlphaGo, this game from DeepMind. And there are two networks here. One's called policy net, the other called value net. So it's a very good and successful use and also successful pick of the specific tasks. So feel free to check out the paper. So after AlphaGo and DeepMind push it, revise it into something called AlphaZero. So AlphaGo is trained from the masters. So the Go masters historical moves, and you use those to train your policy net and value net. And AlphaZero, it's removed the human historical data. It just have two agents, two computer gamer, gaming with them each other. That's called a self-play. And AlphaZero, it's just another revolutionary move from AlphaGo. And you can actually tell from this figure, the downward figure, and just after a few hundred steps, AlphaZero without anything, with no historical master data, it reaches the performance of AlphaGo, so which is really great. It's a very milestone work. Okay, so if you want to learn reinforcement learning, check out this website called OpenAI Spin Up, and this is the best place. And there's really no other place like as comprehensive, as clear as this one. And they have good tutorial and good resources, and also very good benchmarking. Okay, so that's the first 4 trend. Now let's talk about the 5th trend, is learning to learn. So what do we mean learning to learn is, so it really goes beyond the traditional training test and from same distribution data assumption. And your task, the training and the test, the tasks in the training and the tasks in the test actually are different from each other. So this is what they mean learning to learn. So for example, you have a dog detector, and hopefully you want it to be able to detect maybe a cat. So that's this kind of formulation. So this is, if you think about this learning to learn, is a smaller version of something called artificial general intelligence. This is a very heated word like AGI, right? So people kind of saying the current AI or neural network models are only good at narrow AI, which in cases the tasks itself are very well defined, like medical imaging diagnosis, game playing, all this. But you have a very clear goal. But if we think about human perform many things without a clear goal, and it's mostly autonomous. So how do you achieve AGI? So it's a very noble goal. It's also kind of blurred and vague. It's pretty vague, to be honest, because what do you even mean general intelligence, right? Because dog has its level of intelligence, and dolphin, parrot, and human. So do you mean human intelligence is AGI or it's superhuman? But I still want to talk about this word because people talk about this a lot. So it's a very vague definition of defined field. All right, so now let's move to training workflows. So there are, I picked 3 very novel, important workflows so to talk here. So the first trend workflow is called layer-wise pre-training workflow. And it depends on the self-supervised type of loss formulation. So I think hopefully you know what is an autoencoder. It's really just you have an X input, you project it into a mostly lower dimensional h smaller space h and x to h, and then using h to recreate x hat, and then you try to learn the h by minimizing x hat and x differences. So of course you cannot just do a blindly simple vanilla version like this. You have to add a lot of different kinds of regularization, different kind of tricks to kind of push that hidden layers to become good, reliable feature detectors. So this is called reconstruction loss. And there are many variations, like I said, there are variational AE, denoising AE, sparse AE, there are even more. And here I just show you the decoder and encoder are using this feed-forward MLP formulation, but you can just replace that into a convolution neural nets. So the most classic is this deep convolution inverse graphic networks. They just replace the encoder with a CNN, decoder with a deep convolution network, but still the same workflow. All right, so now let's talk about this layer-wise training. So you can train this layer first, then second layer, third layer, and every layer just guarantee a good training first, then train the next layer. So basically, this layer by layer training forced to learn good features that describe what comes from the previous layers. And how do you use this? I mean, so this is a very classic pipeline, so called unsupervised pre-training. So you use our original data and pick a good starting point and train each level in a greedy way. And then you train first layer fixed parameter, then train second layer fixed parameter, then onto the nth layer. And when you have a really good model, of course, each one of this learning is guided by some unsupervised or called self-supervised loss formulation. For example, reconstruction loss is one of that. And then you use all your label data to use everything you already trained and only fine-tune the weight and also this last layer you added for your task. And this is called pre-training, layer-wise pre-training, then plus a fine-tuning for the supervised task. And this is extremely good workflow. And so the reason is what? So I'm not going to jump to details. And essentially, it's because deep models training is very tricky because of the non-convexity and also because of map vanishing gradient problems. All right, so that's the first workflow, and that's our trend 6. And now let's talk about trend 7. And this is a very innovative and milestone workflow for sample generation task, which is the GAN. So GAN is selected as the top 10 breakthrough technology in 2018. And essentially, it's a workflow. It's not specifically about topology. So it proposed I have a G is a generator. I have a discriminator. I'm trying to generate samples. In this case, it's this X on the right. And then also, I feed my generated sample into the discriminator. And also, I feed a sampled, just get it from the observed true data into that discriminator too, right? So now I am trying to train both the discriminator and generator. I'm trying to train this really, really good discriminator that can distinguish the this generated data versus true data. But when I'm training my generator, I'm trying to make my generated sample as similar as those observed samples. So my discriminator just cannot distinguish generated and the true samples. So which is really interesting if you think about it. So in the end, you're using this bi-level optimization to get to make your generator can generate samples that are just so good. It's almost just, there's no way to distinguish the generated sample versus the true sample. And this workflow kind of revolutionized many of the generation applications. For example, this is called a style transfer. You try to create this image of actor's face image into a cartoon style. And also like something called cycle again. You try to borrow this zebra's texture into a horses and the summer sceneries into the winter, but it's all the same picture. And the other important milestones called progressive GAN, which generate really good quality face images, has very high resolution. And then recently, there's a breakthrough is this called the style GAN. The style GAN is from CVPR 2019 from NVIDIA. So there are only two. So the only true images is the first row and the first column. So what this is trying to do is just to pairwise, so look at this. So this is this man's face and this women's face. They do a style. It's kind of a composition of the two styles into on this man. There are also different level of style transfer. So this is higher, it's much bigger transfer. Lower, it's much smaller transfer. So if you look at this, the last row, and this is still this women's image, but it transferred the hairstyle from all these different columns. So it's really powerful, exciting, and very powerful and exciting. Okay, so this is the trend 7, the generation through GAN workflow. Now let's talk about the third very exciting workflow called AutoML. So essentially, designing deep learning topologies is very difficult. It used to be more like art. I mean, how do you know how many layers, how many layers, what's the hidden size, what's the future size, and so on and so forth. So this propose a very principled meta task, which has a controller, and the controller output how many layers. Controller predicts how many futures. Controller predicts what's the future height, what's the future width. So if you think about it, I'm having a higher level neural networks trying to learn what's the best topology parameters. So which is very powerful, but also, of course, very costly. And then people also extend the same idea, this controller idea, to learn what is the better optimization, because you have so many optimization choices to make. So that's very similar idea. So we finished the workflow, 3 workflows, and now we are reaching the, I'm trying to speed up and to finish. So now we are in the trend 9. It's the different metrics to evaluate deep learning models. So we used to, people just use Y truth and versus Y predicted, the differences of the two, and to measure how good your model are. And this is the classic like accuracy F1, that type of metric. But it becomes more and more less like not enough, because deep learning model now kind of pushes into every possible technology, right? It has so much interactions with the human users. And then to guarantee certain level of trust and transparency, we have to make it more interpretable. So here I list a overview of possible method. Like we can think about group the interpretation method into two kinds. It's post hoc analysis or inherently interpretable model. And in the post hoc analysis, there are feature visualization, feature attribution, or feature or combination. There's also training example level attribution. So the picture I selected here is from DeepDream, and they're really the one to pick to look how to interpret the deep learning model. Doing their website, it's really great to explore. All right, so then another metric is the robustness of deep learning model. This is a very classic example called adversary examples. And then you have original image like a panda, and then you just add in this a nicely crafted noise and very small noise, and this is the generated image. So for human eyes, this is completely still panda, but this will be predicted as given by the deep model. So this kind of create a whole subfield inside deep learning or machine learning is the robustness of the deep learning model. So those models seems to be really powerful, but they're so sensitive to this this type of noise. So feel free to check out related paper just using adversary example to search. And similar, and there in this there are more examples. There are just many more like this type of adversary examples. All right, so then people start to use verification to think about, okay, so can we just try to verify? And some model may be probably robust. So there are also a lot of work here. It's a very hot research topic. Okay, so that's 9 trends already. The last one, and I'm going to finish and wrap up here. So last trend is this hardware adaptation. So essentially, there's also, I'm not covering anything about designing hardware for deep neural networks, but there are many industry doing that, like a GPU type, right? There's so many embedded devices designed only for deep learning. What I will focus here is just, okay, so I have my edge devices, a pretty generic architecture, and can we compress those really great models that has been shown to work very well on the GPU or those big memory settings, and then push them into edge devices. Okay, why do so? Because I think maybe you already you heard about this or noticed about this, and also our department is it's really the leader in the IoT design, right? A lot of IoT related linking technologies. So our life, it's more and more digital. So used to, it's more physical. You have to physically live there, right? So attending a conference by yourself or whatever, but now everything's virtual. And with the virtual, and then means what? It means everything is digital. Everything is you don't need to physically be there, and it's really about those connecting devices. But those devices are not as powerful as a memory rich compared to our regular computer or laptop setting. So can you enable drones to do object detection, enable Alexa to perform really great speech exchange? So how do you do that? Because of the memory energy and computational threads are limitations. And we should compress important models and push them into smaller and less powerful device. So here give you a 3 category of method. So there are model pruning based, there's composition based, you just try to simplify some of the blocks. There's the last is quantization based. So most of the weights are saved as double or the float. Can I save them, can quantize them into binary? If it's binary, I can just use bit to save that, right? And this just will dramatically reduce the memory cost. But will the memory reduce influence the performance? How do you make sure it's not, or maybe approximately not? So there are many exciting research going on in this direction. And here, this is a proning. You can prone edges. You can also prone neurons. So feel free to check out the paper. And so this is a graph from Google Brain's efficient net. So efficient net here, you can actually see this is the red curve, and other here it's all those very important current powerful deep learning models like ResNet 101, the SENet, and so on and so forth. But you can actually tell their number of parameters are all in the hundreds of millions. And then the efficient net trying to compress and just make it much, much smaller in terms of the memory cost, but with better performance. Yeah, so feel free to check out the efficient net. I think I covered everything I want to cover. So there are totally 10 trends, and you can segment into 4 modules and into 7 like orthogonal variables. And this is the references, and I think I'm done.